Hello, welcome back to another Commodore programming basics stuff. Now we left off last time with Advanced Basic. These times we're going to Chapter 6, Color Graphics. So what we'll be doing is nothing fancy. We're not going to be doing sprites or anything like that, or drawing pictures. This is basically manipulating the colors of the characters and of the screen, and to do some bars and stuff like that. We are not going to be doing like sprites and whatnot just yet. But before I go any further, there's going to be two things we're going to be using today, which is very important. We touched one last time, which is the character code. Now we could use changing the color in this in Commodore Basic is certain characters do it, and I can do a brief demonstration of this right now. Whoop. There we go. Ahaha! Alright, I'll just hide my lovely face. So if I go 10, whoop, come on, give me my keyboard. Whoop. 10, print. There we go. Okay, so we do this. We go Control 1, R, Control 2, A, Control 3, I, Control 4, N, Control 5, B, Control 6, O, Control 7, W, and we close that off, and we just print, and we just run it. Sorry, I lost my mic there. Stay, thank you. And we do run. You see, it's just changing the text colors. That's all. Excuse me, having a draw drink. So basically what I'm doing is putting in these characters here. These characters in this context will change the color of the text following afterwards. So you see what I'm getting at. But what we'll be doing, instead of inputting them like this, like it says here, Control 1, 2, 3, 4, 5, 6, 7, we're actually going to be using the character codes themselves. So we're going to use the code. At this point was ASCII. I'm not sure if it's ANSI. I think it's ASCII with a few bits added on from that Commodore added on for their things. And there is a character codes in the appendix. Ah, yeah, here we go. Okay, so screen code. No, don't want to peek and poke. Don't want all that stuff. Sorry. Where's the character code? Yeah, ASCII and char codes, or character codes. So, yeah. I don't know which ones are which, but print's a character, but print's orange. There's one. Not helpful. Not at all helpful right now. Doesn't tell me much what the character codes are. Well, I can see them here, but look. There's no colours. I've got brown, light red, grey. Oh yeah, so there's colours in this prints column, but I have to go through all of them trying to look for them. That's just weird. So we've got that. We've got a colour memory map. Oh, okay, cool. There's that, but there's nothing else. And it says here for me to... Before you read in this section, please take a look at Appendix F, which lists the car codes for all the keys on the keyboard. As you've looked over the character codes, you'll probably notice that each color has a unique code. This is just all colors, blah blah blah. So where's Appendix F gone? Yeah, sprite priorities, I don't want that. Don't want sound, we're not at sound. I know a lot of people watching this will probably want me to do sound, but yeah. Okay. I don't know. I really don't know. It just doesn't say anything. It doesn't do anything. I don't know. But that's only this character code thing is. Yeah, it's folly. It's bullcrap. We don't need to do anything about that. But for the sake of time and whatnot, yeah, okay, we've got characters. We can say use a certain character, say change this to this, change this to this, change this to this, blah 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 blah. We don't want to do that. The second thing I wanted to get into, which we will be doing in this, is peaks and pokes. Now, programming in general, especially low-level coding like we're doing here, which is pretty close to the metal. I'm not talking about web coding or anything that nonsense. I'm talking like full-on low-level C coding, like Linux kernel coding, or hell, even Blender coding for that matter. Peaks and pokes in all these coding languages, so these low-level coding languages like C, C++, and all that. Not C#, maybe Python. To get the CPU to do what you want it to do, you got to put a certain value into a certain address in memory. Especially with these 8-bit machines. These 8-bit machines, everything's in memory. You just got to put a value in memory where something expects it to be, and something will happen. Especially when you're coding for things like the 6502. Which, hold on. This is my C64, which we'll see is this lovely long chip here is the 6502. Except it's not, it's the 6510, which is the more advanced version of the 6502, which is mainly used in Commodore products. Then MOS Technologies, which was owned by Commodore, didn't let these sort of chips out in the wild. And while we're here, we've got the PLA, we got some the ROM chips here, which what we're seeing here, screen, characters. So all the characters are baked into these chips. The CIA chips, I think. And this one down here is the big one. That's the SID chip. The VIC-2 chip is under this can, which I don't want to get off because that's all high voltage, high RFS. Same with this one up here. So, yeah, lovely shielding, cardboard. But in this chapter, which we're going to do now, is peaks and pokes. So we're going to put a bit of a colour, put a bit of what we're going to do is we're going to put a value in a particular memory location. It's not really a register, it's a memory location to make things change. For instance, I can do a very quick one here. So if I go poke 53, can't use a numpad. 53280 with, say, I don't know, 2. If I do that, see, the border changes colour. So I just put the value 2 into there. Now if I was to have a look at that, which is a peak, poke is poking data into memory. Peek is looking at the thing. Pretty self-explanatory, as you'll understand. But there's a little bit of a issue with this. Peak was a 53. We're going to peek at the memory location 5380. But oh, hang on, I've got to go this. Sorry, got to do this. Otherwise, peak, because I touched the numpad. God damn it. Peak 53280, which is what I've done. But we've got to do and 15. Okay, list. Oops. list. Oh, never mind. So if I go this again, go peak. Okay, 5, 5, 3, 2, 8, 0. And we put an and after it. Oh, for God's sake, stay up, microphone. Stay there. I wonder where my little Randy thingy went. That held you in place. And 15. 2. Okay. Why the and 15 here? Well, the thing is, this memory address only takes a nibble. It doesn't store, even though I believe it stores it as a byte. Hold on. Peak looks at the whole byte at that address. However, the colors are only half a byte. They're called a nibble. So 4 bits is a nibble. 4 bits is a nibble. 8 bits is a byte. Yeah. Okay. And you have to learn that a lot when you're doing 8088 coding, stuff like that. You have to add N15 to your peak statement. I don't understand. Okay, it's called a nibble. To peak just this nibble, you have to add the and15 to your peak statement. You'll get 15 as the answer because the last border color poked is grade 3, which is 15. I don't know. Currently variable. So what do we see? So if I go do that again, go peak. Oh, come here. Peak 53820. Let's just do that. Let's see what we get. Out of data error. That's weird. Oh, because it's trying to read 8 bits, but there's only 4 there. Fair enough. So far, according to this, hang on. Let's have a look. Here's something we can do. Let's do a little coding program here. All right. First, I'm gonna go new just to clear out the memory. So let's go 10 for BO. Sorry. 0 to 15. Whoop. What's happening here? For B. Oh. Okay. Look, I'm gonna do a full reset on this because this is getting annoying. Just do a hard reset. That'll do. So just go new, clear out whatever you're there. Okay, 10 for BO equals 0 to 15. Next one. So 24 BA equals 0 to 15. So this is going to do some randomizations of both the inside color and the border color. So if we go 5, 3, poke, 5, 3, 2, 8, 0, comma, BA. Yep, that's the right way around. 40, poke, 5, 3, 2, 8, 1 with BO. Smelly. Okay, 50 for X equals 1 to 500. This is a really crappy way of doing delays. Next X. Okay, 60. Next BA and next BO. Run. Now this should just change the colors, cycle through all the colors. Okay, so it's doing the borders first. Then once that's all done, See, there's only 16 colours in this system, unfortunately. So it's going to go through all the border colours, then change the inner colour, then do the border colours again, change the inner colour. Border colours, change the inner colours. So you see, what we are actually doing here is actually really, really cool. Because what we are doing is we are actually... God damn it. If I get me commodore back out again. What we're actually doing is actually putting memory from here, from the ROM here. We are taking this stuff here, and we're putting them on some of the, I think, no, they're all glue logic. Where's the memory chips on this thing? Oh no, I think it's these ones here. Down here. These are all, we are putting data into a memory address on one of these chips. Now what happens is this VIC chip under here reads this memory address on every step and goes, right, what color do you want me to be? It does that, pumps it into the RF switch here, or S-video, or whatever it is you want, and displays on screen. So what happens, actually, I should point out, is this says, this thing here says, go put memory, put a, saying go put this in, I'm not sure. This says go put this value, which is whatever one we're up to, say 2 or 4, go put this into the memory address down here. This reads it and then pumps it out. So there we go. Reads its display memory. So this one, sorry, I should explain this again, sorry. This, the VIC chip, reads its screen and color memory at every cycle. See this, while the C64 is running, this is constantly being hit. This here, it is constantly going through. Boom, 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 boom. I don't know where all the crystal is, so I can't say what it is. I don't know what hertz it is, so it's constantly being hit. Boop, 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 boop. So it's constantly doing its instructions. So boop, 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 boop. Color's changed. Move it over here. So oh, I got a new instruction. 9 times out of 10, 90% of the time, it's just sitting there doing nothing. Okay, just show what's on the screen. So it's going boop, 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 boop. I've got to change memory. Put it down into here. Da, 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 da. Then on that cycle, after it's done that, this is the exact same cycle of the CPU. It goes over here. The VIC2 chip reads it, reads its screen and its color memory, what it wants, what you need to display. And it does that at either 30 or 25 frames a second or 29.999999999 if you're NTSC and you're weird. Okay, so that's basically how it's done. So it's really cool to match up what we're doing on screen here by putting that value into memory to the actual physical stuff here. So that is really, really cool. So I'm going to put my mug down again, because our program has finished. So what I could potentially do, not really, because I can't change the color of the text that's already there. So basically what we've been doing so far is just printing, doing logically, going pop, 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 pop. But now, what we can do is what's called screen memory. Now this is the map of what the screen is. So this is what entirely what the VIC2 chip sees in memory. So it sees a grid like this and goes draw line by line by line by line by line by line on every cycle of the CPU. So it draws top to bottom, left to right. So sorry, left to right, top to bottom. My bad. So there was various little tricks that were done. So every cycle goes da 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 da. Whoop! I get an interrupt here. Change the memory. Da, da, next line, change the memory. Next line, change the memory. Next line, change the memory. There's actually a fantastic talk on this, which I'll probably link down below, down below, is the Ultimate C64 talk, where it goes into this a lot further. Now, if you don't know how CPUs actually work, like the ACU and all this stuff, if you don't know what registers are and all that, then most of the talk will probably go way over your head. You probably won't even understand what's going on. For fun, I'll also put in the Ultimate Gameboy talk, and we'll go from there as well. But for now, let's get into some real heavy duty stuff. Let's get into the screen. Let's fuck up its memory. Sorry if you're that way inclined. Okay, so let's do a reset here so I can get my colours back. Now, I see a lot of kids when they see this system, oh god, why is it blue? Why is it all this? Well, the simple reason is contrast. This is blue like this. The same with the original Mega OS, was blue with yellow and white. It was to increase the contrast because you're watching on a nice clear LCD screen. But on all the old fuzzy CRTs, this was quite hard to read at times. But now, it ain't so much. Because it ain't so much of an issue. Back then it was. So you had to make it really stand out. Make the text really stand out so you can read it properly. Okay, so... that's weird. No, okay, go back up here then. Alright. So basically what it is. Okay, let's have a look. Let's have a read. Okay. The 64 screen can hold 1,000 characters, 40 columns by 25 lines. So there are 1,000 memory locations set aside to represent what is on the screen. Imagine the screen as a grid, 40 by 25, with each square standing for one memory location. Each memory location can have 1 or 256 different characters the 64 can display. See Appendix E, thank you. Poke each of these 256 characters is represented by a number from 0 to 255. If you poke the value for these characters into a specific screen memory location, that character will be displayed in that specific screen location. Here is a grid that represents your screen, complete with numbers for each memory location. So let's just stuff it. Let's go. Poke. We've got a screen memory, so let's go right in the middle. So, so we got down in the middle, which is 1424, and we want to go into the middle of that. So we add 20 because it's half of 20 columns. So what is it? 1424. So we go 1444. Okay, 14. Whoops, I did it again. 1444. Because we added 20 to 1424, which is way at the end. Well, let's just put, say, I don't know, 130 into there. Let's put that in there. Let's see what we get. Here we get the B, right in the middle. So you see, I've just poked some data into a memory location. The VIC-20 read it and plonked it right there. So let's go again. Let's do another one. So we'll go poke. I don't know. I'm just looking at it here. So 1, 6, 48, 60. And there we go. There's another one. Put it right there. So that is pretty cool. When you actually think about it and you're going, I'm actually putting data through the actual chips here. I'm not using an abstract layer or anything like that. Like you do with most coding languages today, especially web coding. You've got so much crap between you and the thing, and you got to go through the servers, and it does all this. Blah, 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 blah. I hate that. So it's saying here what the best way to do this is not do the same thing like I did, is just put the memory in like that. So what the best way to do, it says here, is you do a point. You set your point, so you got your start, which is, in this case, would be, I don't know, what one? Well, this top one was 1424. You'd say that, then you go, Yeah, so you basically don't use hard-coded values essentially. So, well, now we've got a color map here. And more bouncing balls. But basically what we say is, we've got a point, so we go 10 point equals, well, we'll do something here. We'll go x equals, let's say 1424. Okay. And okay, so we go next, we got 20, and we'll go y equals, go 0. Just leave it at that for the time being. So 30, we're going to set our coordinates here, so we go point equals our starting location, which is x. I've done this wrong. So we'll go 5. 5. Start equals 1424. Okay. 10. X equals 0. Just leave it at 0 for the time being. And from there, we build our point. So we've got point, so where was I up to? Say 30. Okay, 30. Point. So basically where we want to actually put this thing in is our start, which is start plus, then we've got our x location in screen, which is x, and our y location, which is plus our y location, which is 40 times it by y. Now what this will do, since it is 40 across, so it's 39, it's 40 characters across. So it's going row, 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 row. This one's easy. It's like how many characters across. Boom. Then we've got to go how many rows. Now there's 40 memory points per row, so we go number of rows times it by 40. We'll do that. So now we've got to poke. So hold on, 40 poke point comma, I don't know, 50. Now let's run it. Oh, go list. Sorry, let's just make sure we got our everything correct. No, we don't, because this thing's floating there. Okay, so we'll go 10 x equals 0. Cool. Okay, let's list our memory program once again just to make sure. Yep, that's our start, that's our x, that's our y, blah, 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 blah. So if we run this, we should get something at 142400, so 1224, which is right about in the middle. So if I go run, syntax error in 5. Right, I think that has to be 05. Okay, so 05 start equals 1424. List. Okay, that works, I think. So if I run, syntax error in 5. Bugger. Why are you doing that? I think I've done this a little bit wrong. But anyway, you get the idea. You don't use hard-coded values like I did before. You use dynamic variables like that. This is going really well. Okay, so let's go new, clear everything out. So I'm going to have to do some more bouncy balls. So I'm just going to type out this program again, just so we know, you see how we are actually doing this. We actually are going to be doing an animation here. And okay. Well, anyway, let's go poke. We are going to be doing the animated ball again, except this time we're actually going to what was I going to say? No, I've forgotten. Anyway, we are actually going to do it with memory locations rather than hacking text back and forth. So let's do this. We go poke 5, 3, 2, 1 with 1. Not going to print anything. Bugger off. Oh, better do this. Print. Let's control white, which is control 8, I think. No, control 7 is white. Then shift home. Okay. It's going to set the text to white and clear the screen. That's understandable. So it's going to set one of these, the screen memory. I don't know what that's at. Oh. Oh. I messed that up. It's supposed to be an 8 here. 2, 8, 1. Come on, 1. Print. Because I keep using these numpads, it's annoying. So control white, which is control 7. And shift, clear home, or just home in this case. There we go. 5, 3, 2, 8, 1. Yep, so it's going to set the border color to 1. And now we're going to set the inner color to something else. So I got poke. 5, 3, 2, 8, 0. Boop. 7. So memorizing these memory maps is interesting. What do I have to say? Oh, so this top line, this top line resets the color. Now this one here sets both the border and the inner to 7 and 6, whatever color they are. I don't know what they are. So here we go. So we go, okay, 30 x equals 1. So this is basically what I was trying to do before, but I kept getting a syntax error for some reason. Y equals 1. 40 dx equals 1. dy equals 1. 50 poke 1024 plus x plus 40 times by y comma 81. So then now it's changing the screen address and it's going to put 81, which I'm assuming is a circle. So it's going to put it out. What we've got here is x, so we've got which is the root. This is the, this is the root. Sorry, I'm just going to show you for a tick. Okay, if you see closely, up the top here, it says 1024. That is the top left of the screen. So that's the memory location right there. So we're going to start there, and from what I gathered, we're going to loop through this from one screen to the next, and we're just going to go boop, 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 and do our thing. Okay, so, 50, and it's going to put character 81, which I'm assuming is that. Okay. So we go, okay, sorry, wrong thing. I'll get rid of my mug. There we go. If we go 60, 4t equals 1 to 10. Next. So doing a little bit of delay. That's fine. So poke 1024. Okay. Don't know what they're doing, but okay. Plus x plus 40 times it by y, comma 32. So we're going to be changing the character after a slight delay at that location. Okay. I don't understand what's going on. Oh, okay. Now I see. Oh, damn it. Yeah, I don't know what to do. So let's do this again. Poke. 10 poke. 5, 3, 2, 8, 1. Control 7 and control home. 20. Poke this address again for me. 5, 3, 2, 8, 0, 7. So when I was growing up coding on this, I didn't really fully understand it at the time. It wasn't until much later when I was actually trying to do some low-level stuff with Linux kernel and stuff like that. Actually, all this really came together. And with Blender a lot as well. Used a lot of memory functions on that. X equals 1. Y. So, this don't feel bad if you're not following it very well. Granted, I'm not the best of teachers. I'm stuffing up many times. And yeah, granted, I'm not the best of teachers. And I'm probably not explaining this overly well either. God damn it. I hate that. So used to holding down shit. I did it again. DY for capital letters. But the thing is, on this C64, it's always capitals until you tell it otherwise. It's high. Yeah, there's two character modes, I should say. You've got the capital ones and you've got the small ones. That's why every game on the C64 has the same text. You couldn't really load your fonts into memory because there was just not enough memory to do so. There's only, for this basic, there's only like 64K for basic. So, yeah, so best of luck getting a full font in. Some did do it by using clever loading techniques. Let's not forget, this machine was being built and sold right up to 94 when the company went bankrupt. So there's plenty of stuff going on in those years, including like Mayhem and Monsterland, which has fantastic scrolling colours. It's like Sonic for the C64, for goodness sake. Something no one thought was possible. Not at that speed. And you also had like the Great Giant Sisters with their fantastic scrolling. And other things like that. So techniques and everything did get a lot better as time went on. For, what is it for? T. Alright, equals. So what I'm doing here was very basic way back then when, what was it, 84, 85 when this book was printed? I don't know. I can't remember. So this was very basic, but that was the way of the times. That was the times. Did that like this. The C64, the VIC-20, the yeah, the Spectrums, the what other 8-bit machines at the time? There was a lot of them. A lot of the which a lot of your American viewers would probably not know a lot of these machines because they weren't all that popular in the States. In the States, during the time of the C64, the Amiga, Atari STs and stuff like that, even the Atari 400 and 800, all that was in America at the time that anyone really cared about, there was two machines. That was the Nintendo Entertainment System, or the NES, more appropriately known, or Famicom if you're that way inclined. It was either the Nintendo Entertainment System or an IBM. All the micros of the 80s that myself got to experience, as do anyone in the power regions, all in Europe and all that, we all experienced these machines. Because the computer crash, that people say, oh, there was a huge computer crash, I was thankful that we survived it and all this going. No, there was no computer crash. It was just in the US. So, yeah. Or x is greater than or equal to 39, then dx equals minus dx. Now, okay, we're up to 100. Y equals. So at the time when these machines were being popular, like the Spectrum, C64, a lot of people would do their programs the exact way I'm doing it now. I'm reading the book here, I'm reading the program, and typing it in. There's many a story being done on the Specky, the ZX80s and stuff like that, where people were just copying the programs from magazines. However, some of them had typos and they didn't work. But it was because of that the magazines were putting these programs out. It's what kickstarted what is known as the was a bedroom coder boom, where all these kids doing programs and games or whatever in their bedrooms, and then either publishing them through magazines or sending their tape off to a distributor who says, oh yeah, we'll have a go at that. We pay you this amount of money. That's where people like Jeff Minter got his start. The Stamper Brothers, who later formed Rare, they were Ultimate Play the game at the time. They were fantastic coders. And so many of them. And we've got fantastic original games like Jet Set Willy, Ad Attack, just Gauntlet, all these other cool games. Even the biggest game of the time, which was Elite. Yes, the forerunner to Elite Dangerous these days, that is known as today, was coded in the bedroom. On a BBC Micro, no less. So I think I have our program coded in here. Now what we got here, it's going to clear the screen and set everything to white. That's what that does. Compared to whatever it was in there, it's just going to reset this thing, put it into an initialized state. Now that's a good thing to do when you're coding, is to initialize your variables and the stuff that you're going to use. That way you don't get things confusing when whenever you're using multiple programs together and stuff like that. So make sure you have a definite bed of foundation for your program. Now what the second line does, it changes the color of both the border and the inner here. Then we've got our variables here, x and y, and dx and dy. What these are, these dx and dy, is your delta x and delta y. So basically, how far across do you want it to go? So how quickly you want it. So how quickly do you want it to go next on each step? And at this point, it's just going to go once. So it's going to go one character across. Pop, 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 pop. If I change that to say, I don't know, say 5, it would go. Brr, 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 brr. And the same with y. It's how fast down it goes down here. So we've got x, which is 1 at this case. Y, which is 1, so it's going to start up here. Set it to 81. Set the character 81. Then do a little delay, change it to another character at that same address. Now this is it. We shift X variable across by dx, which is 1. So it goes across like that, does a little check. If X is less than or equals to 0, so if it's back here somewhere, or if it's greater than 39, which is over here, then go the other direction. So just go back. Start going back. Now, y equals dy, so it's going to offset it by that on every run, so which is 1. So it's just going to go down 1. Then when it goes, then it's going to check, is it up here or is it down here? If it's down here, bounce up. If it is up here, go down. If it's up, go down. So what it's actually doing here with this minus dx is actually inverting it. It's not putting a minus symbol in front of dx. It's actually saying itself minus itself. So it's practically inverting it itself. So dx, so it's minusing itself. So okay. So it starts go back up that way. So if I do a list, just to make sure everything's right. Yep, print, poke. So if I was to run this, we should see that this will clear this, set everything to white, and clear the screen. Okay, so we do this, run, syntax error in 6D. Okay, so here's the real thing about this stuff. In 60, so what did I miss? 4t equals t equals, okay, 1. Oh, don't do this to me, for God's sake. Alright, do it this way then. God damn it. 1 to 10. Then we go next. There we go. Close enough. Okay, enter. Now if I'll go back down here and just go to list, that should be fine. Yep, 1 to 10. Okay, run. And it's going boing, 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 boing. That is really cool. So we've got a little bouncy ball. Just, it's not using real physics, it's just going, hang on, I'm over here. No, go back the other way. Go back the other way. There we go. That is pretty cool. So it's not actually using physics, it's just saying, hang on, I'm outside this, go the other way. So that is really, really cool. Okay. Ball's going out of the bounds screen. If we add a little intelligence to the ball bouncing program, so far the only thing is checked is whether the ball's gone out of bounds on the screen. Try adding the following words. Okay. Alright. Okay. So let's do this. Okay. List. Okay. So what we're going to do, we're going to add a few more lines. So we're going to go 21. Whoops. 21. Now doing this, we'll just insert it into here. We'll just insert it into memory. So this is the basic memory. I don't know how to check how much memory I've got left, so we'll just take our chances with this. 1, 2, 1, 2, 10. I'll go 25. So when I press enter, it puts the line into memory is what I'm saying. So I go poke 1024 plus the integer, which basically means the whole number. This I should explain the whole number of this random number. Okay, random 1. What is it doing? I don't know. Okay, 1000. Okay. So what an integer is basically is a whole number. So like 1, 2, 3, 4. If you want your how do I put this? If you want your decimal places and stuff like that, you've got to use what's called a float, or decimal, or double, depending on what it is. And JavaScript is just number, which is weird. JavaScript's weird. PHP is weird. Any language that has anonymous variables is weird. And by that I mean variables that do not have a data type attached to it, where it's up to the interpreter to guess what type it is. And that can lead to all kinds of weirdness. Even though, which is like why I love using C and Python and stuff like that. And even C# for that matter. Even though you can kind of use anonymous variables in there, then again you can't. It's just weird. But I love C coding. I love stuff like that. Because I really love this sort of level stuff, like really down to the bone, down to the metal coding. It is like, you can really... This I'm doing here is basic. Okay? It is basic. Then dx equals minus dx go to et. Oh, go tot. Nope. To 80. Okay. I have no idea what this is actually going to do, but I'll put that in. A list. Let's see what we got now. So I've added a couple lines here. This 21 is going to do an L, and it's going to poke just a random address, because there's only 1,000 characters, so it's never going to go above 1,000 characters. So it's going to put in random addresses this what's called a reverse space. Whatever that means. That just goes, what's down the bottom? 27. I didn't do a 27, did I? No, I didn't. Okay, 27. Next. L. I thought I did. Okay, I must have typed it wrong. Yep, okay, cool. So now it's going to put a reverse space in random characters all over the place. It's going to put 10 of them. Okay, this is basically going to put some obstacles in the way of our ball. Now down here, that's what it's doing down here, is it's going to take a peek at where we're at, basically. If we are there and it's going to equal a character, then it's going to say, oh, hang on, bounce off it. Then go dx equals that. So invert itself, then go back to 80, which is there. Then go, then do its thing. So then this doesn't count, it's false. Okay, it doesn't go to there, but then it goes back to 50 and repeats itself. Sounds simple enough, doesn't it? So basically what it's doing is creating some random obstacles, and then it's peeking from where we're at, basically, where we're going to go, I should say, which is that, where we want to put it. It looks at the memory. Does it come out as this? If it does, bounce back. Fair enough. So basically this is what we're seeing here. We're poking memory, we're putting data into memory, then we're looking to see what that memory location is. If there's something there, do something. So then we go run and hope for the best. Okay, so it's only put one there. And it's never going to hit it. What? Okay. I'm supposed to put 10 of them. Breaking that. So list. I think we might have made a boo-boo here somewhere. I'd have to. It's trying to do 10 of them, but it can't. What have I done wrong? Have I done wrong? No, I have not done wrong. Let's run it again and see. Unless we're not still doing that same thing. It's only putting one of them there. It's not actually doing anything in the random. Huh. Maybe. Maybe. Let's do some more. But it is cool we're actually directly addressing screen memory and stuff like that. And we're putting a little bit of logic into it, which is really cool. So from L1 to 10 equals 1 to 10. Poke that plus a random number between that. We have to use an integer because otherwise it will come out as a float, as a decimal number, and can just be weird. I think. I don't know. Why is it doing that? It's not working at all. Oh, anyway, let's see. Can I? Okay. Oh, God damn it. I should not have tempted fate. That's weird. Okay. Oh, well, just run it anyway. Okay, so we failed. Then this book has failed. Why did this book fail? Okay, let's have one last look. Come on. What are we looking at? We're looking at this 25 line. And I know what I did wrong. RND, not RAND. There we go. Now if we run it, we'll go list. One more, just to make doubly certain, because you have to do on these old things. Yep, okay, now run. There we go. And it's still not doing its thing. Oh, no. Oh, it's hitting it. And it's clearing it. Weird. I think I know what I need to do. Yeah, I know what I need to do. Okay. List. Okay, so I need to change this. Not to 166, but to 160. Hopefully that will work. So let's see if it hits something. Nope, it's not hitting anything. Come on. Oh, come on. This, oh, syntax error. Okay. So, okay. List. I'm going to have to write the whole goddamn thing out again. Okay. Then dx equals minus dx. Go to 80. There we go. That should do it. This, just to make certain of it all. Yep, looks like it's all right. I'm going to change this bloody background color. Ugh, it's yucky. It's icky. Change it to say, what colors we got? Let's have a look. Okay, so we've got some colors here. Go 0 for blick. Make it blick, I think. And then we can change the other one to say orange, which is 8. So let's run this and see what we get. Syntax error and 20. Oh, God damn it. Now what? There's nothing there. Oh, I think I know what I've done wrong here. Okay. Syntax error in 20, I believe, is because missing a semicolon. Oh, or colon, I should say. There we go. That should be right now. So we go run. Oh, there we go. It's black and orange. So simple little stuff like that. Simple little adjustments, and it works. If it actually hits something, please hit something. There we go. See, look, bouncing off. It's just that this book was wrong. Now I was going to say, back in the Coda Boom, and it's broken. Oh no, it's right. It fixed itself. So back in the bedroom Coda Boom, back in the pages of when programs were being done, a lot of them contain errors, and a lot of the cool stuff of programming like this is figuring out what those errors were. Like I just walked my way through this program, saying what works, what doesn't, and it turns out what was wrong in this book. It was wrong in this book, and I'll turn myself back on for a tick. So it turns out, down the bottom here, it says 166, when it should say 160, which I believe is up here somewhere. Somewhere up there. So basically, the book was wrong, but we troubleshoot it. We understand what we're doing now, so that was cool. And we've worked it out. And I worked out some of the syntax errors that I did and stuff like that. And I just noticed on OBS that I've got the taskbars running. Stuff it. People know I'm using an emulator. If people have a whinge, have a whinge. My Commodore's down there and I know why it doesn't work. I accidentally fried the chips because the power supply decides I'm going to put out what was it, 100 volts? Not 100 volts, 11 volts when it should be pumping out 5. So it fried my chips on the board of both Commodores because I didn't know at the time. So yell at me then. But, so with this, we've got our colours and we've got a little bit of peeks and pokes. So we've got a little bit of memory manipulation. So it wasn't really much on colours. Even though colours were related, it's not really much of it. It was more memory manipulation. But anyway, next time, if we do this, we're going to do into the real cooly stuff. We're going to do sprites. Hey! Cool. And look at this. I'll go, ooh, see? Look at this. Look at all this to look forward to. Haha! That's going to be awesome. So, hopefully I'll see you then. The first, I have to say here, right now, that first video, the popularity of it, blew my mind. I was not expecting it at all. It's like, what 30 odd views in a week that I've posted it? Got like 20 odd views in the first day alone. It's just phenomenal. And thank you everyone for watching, and really makes me happy because, well, what's the point of doing YouTube if no one's going to watch it? But with this, people are watching them, and I've been getting a lot of cool feedback from it, and yeah, I'm very happy, and I hope you are happy. And truth be told, I wish for you to go out and do this yourself. Just grab a C64 emulator like this one, which is Vice, just Vice emulator. For Windows, it's WinVice, of course. Under Linux, it's just Vice or X64. And it is, so, trying to find this. Like I linked the manual into the last video. So go through there, go through the stuff that I'm going through right now. And we'll see from there. But let's have a look. What we got? So we're doing some more picks and pokes, but this time we've got data to look at. And we'll be looking at binary. Oh dear. Oh, binary math is not one of my strong suits, I have to say. Well, anyway, thank you very much for watching, and I hope to see you all in the next one. How do I say? Bye-bye, and watch the pretty ball go by. Bye.